In this video, we're going to review the concept of heat capacities and how we could use them to calculate changes in internal energy and changes in enthalpy. So the heat capacity is defined as, we'll abbreviate it as C, and it's defined as the ratio of a specific heat divided by a change in temperature in the limit that that change in temperature is approaching zero, or it's infinitesimally small. And so if we're dealing with an infinitesimally small change in temperature, we could rewrite this ratio as the partial derivative of the specific heat over the partial with respect to temperature. Okay, so that's just the formal definition of the heat capacity. And there's different types of heat capacity that we deal with. If we're dealing with a constant volume system, then we write that the heat capacity CV, where the subscript V refers to a constant volume, is equal to the partial derivative of the internal energy with respect to temperature at a constant volume. And if we took the heat capacity, CV, and we integrated it from some temperature 1 to some temperature 2, what we would end up with is a specific internal energy. Right? And so normally what I do is I signify if we're dealing with a heat capacity on a mass basis with a little hat. So mass basis. Or similarly, if we're dealing with a heat capacity that was in units of joules per mole per Kelvin, I would abbreviate it with a little tilde here. And what we would end up with after integrating it is the molar internal energy, also with a tilde. Okay? All right, and so that's for the case if we're dealing with a constant volume system. If we have a constant pressure system, where the volume is allowed to change, we know that our heat capacity, our constant pressure heat capacity here, Cp, is equal to the partial derivative of the enthalpy with respect to temperature at a constant pressure. And if we integrate Cp from T1 to T2, that would give us the change in enthalpy. And once again, if I use a hat, that means the change in enthalpy is on a mass basis. Or if I use a little tilde, then our change in enthalpy will be on a molar basis. Alright, so we have two different types of heat capacities depending on the type of system that we have. But these two heat capacities are related to one another. So Cp is related to Cv. If you're dealing with solids and liquids, then our change in enthalpy on a mass basis, from the definition of enthalpy, we know it's this. Right? And because we're dealing with a constant pressure system, we know that the pressure isn't changing. Okay? And so what we're dealing with is delta H is equal to delta U plus P delta V. Now, if we're dealing with a solid and a liquid, a lot of times we assume that these solids and liquids are incompressible. And so if they're incompressible, that means that they can't change their density and they can't change their specific volume. All right? And so as such, this second term on the right-hand side is going to go away because solids and liquids we assume to be incompressible. Alright, and so if delta H, or if the PV term goes away, what that tells us is that delta H is just going to be equal to delta U. And we know from our definitions of the heat capacity that Cp is equal to the limit of delta T as delta H over delta T go to 0. Right? But from our argument up here, we could also say that delta H is just equal to delta U. And if we replace delta H with delta U, what we end up getting back is CV. So in the end, what this tells us is that for a solid or liquid, the constant pressure heat capacity is the same as the constant volume heat capacity. Now, if we're dealing with an ideal gas, the story is a little bit different. So with an ideal gas, typically going to talk about moles. And so with our molar enthalpy, we once again apply the definition of delta U plus delta PV. All right. Now, you can see here that now the pressure is inside the delta. So that's the reason I did that. So even if the pressure was constant or if it was changing, this statement is still true. Right? If it was a constant pressure, I could pull it out of the delta. But in any case, the reason I wrote it like this is because we have P and then the molar volume. And we know from the ideal gas law that this is just going to be equal to the gas constant times temperature. Okay? So what we have now is delta RT, right? And so if we take this and plug it into the definition of the constant pressure heat capacity, what we get is delta H over delta T can be replaced by this statement, where we have delta U over delta T plus, we could pull out the R because it's a constant, and we have delta T over delta T. These will cancel. So what we're left with is that, since we know this is a definition of the constant volume heat capacity, what we're left with is that the constant pressure heat capacity for an ideal gas is equal to the constant volume heat capacity plus the gas constant. Okay? All right, and so those are the important identities to know for heat capacities when you're dealing with solids and liquids or an ideal gas. The last thing I want to talk about is, what if you're dealing with a system in which the temperature is constant, so it's isothermal, and the pressure in the system is changing. Right? So for solids and liquids, we once again begin by looking at delta H. So delta H, and I'm going to deal with it on a molar basis in this case. Okay. So that's going to be equal to delta U plus, once again, I'm going to put the P and the V inside the delta here. Okay? All right. Now, with the change in internal energy, this term, we're going to cross it out and say it's 0 because the system is isothermal. All right, so we don't have to look at that. For the PV term here, it's constant temperature and it's changing pressure. So the P, we can't actually take it out of the delta. It's actually going to stay in there. But with a solid and a liquid, we once again can invoke our assumption of incompressibility, and we could say that that molar volume is constant. The reason for that is because solids and liquids are incompressible. Their density isn't going to change. And so if we pull that out of the delta, what we have now is that the change in enthalpy is just going to be the molar volume times the change in pressure. Okay? So that's if we're dealing with a solid or liquid. But what if we're dealing with an ideal gas? How does this analysis change? Okay. So for an ideal gas, once again have a delta H is equal to delta U plus delta PV. Should be more of a tilde here. Alright, so for a constant temperature and changing pressure system, this once again is going to be 0 because isothermal. For the PV term, we could once again apply the ideal gas identity that we used earlier. And this is going to be equal to RT. So we have R times delta T. We pulled the R out of the delta because it's a constant. But what the other thing that's constant as well is temperature. So our delta T here is actually 0 because the system is isothermal. And so what this tells us is that if we have a constant temperature and changing pressure system, that the change in enthalpy is actually going to be 0. And so this is what we see for ideal gases. But as we'll see later on in this course, when we're dealing with non-ideal gases, this result doesn't necessarily apply. In fact, what we're going to see is that the change in internal energy and the change in enthalpy at constant temperature but changing pressure, those are not going to be equal to 0.